in your proceedings, there's a little bit more extensive paper all about logarithms and how they're calculated. But my history of this goes back to the 10th grade when we were taught about logarithms, and we were given this little table, and I asked the teacher, well, how did this table originate? He says, well, your table was condensed from a much larger table that was prepared by the government. So I asked, well, but how did the government how did they actually calculate the logarithm? And her answer was, be quiet or I'll send you to the principal's office. And I later found out that the government tables were actually a major event in feminist history. A lady by the name of Gertrude Blanche was the first woman to lead such a large technical project. And during the dark days of the Depression of the 1930s, to create 100 jobs for clerical workers in New York City. And she put them to work, pencil and paper. And half of the work was creating the logarithms, and probably the other half of it was error checking. But I still to this day do not know the method that she used. And Gertrude Blanche eventually was an interesting character. She was denied security clearance partly after World War II, partly because she was originally from Poland. She lived with her sister, who was a card-carrying member of the Communist Party. And also, the FBI cited she never married or had children. Which meant she may have been, well, we won't go into that. But a certain class of people that were denied security clearance automatically. All right, well, so I just want to say that, let's see, why isn't it going forward? There.
Yeah, you got it.
Okay. So if you're curious, like I was, you can find out more from the paper, and you're always free to contact me and ask questions.
Of course, you won't give us your phone number.
So, this is just one. So what we're going to look at is just one little corner of that paper, and this is all. I've tried to boil it down to elementary calculus, and you know. We all learn in calculus that you can calculate logarithms by this method. And so how can you calculate logarithms by integrating that? Well, it turns out it's not so easy. It doesn't really work very well. And the reason it does not work very well is because that 1 over t function is not very well approximated by polynomials. The usual methods we use to do numerical integration don't actually integrate the function that we're interested in. They integrate a polynomial that matches our function at certain points. For example, if you want to use trapezoidal integration, that actually you're actually taking the integral of a straight line function that matches this function at the endpoints. Or if you want to integrate by Simpson's rule, it matches at the endpoints and the middle, and so forth. And it turns out that this 1 over t is a very, very poor match to polynomials. So integration doesn't really work very well. So one of the questions is there some magical point between 1 and x such that x minus 1 times the 1 over that magical point will be the integral? And the answer is, of course, there is. It's guaranteed by the mean value theorem in calculus. Whoops. So how can you try to find that magical point? Now I have to tell you this. What I'm about to show you, this was originally taught way back in the last century in the fourth interest group by Nate Grossman of UCLA, and it's called Borchards' algorithm. But basically, you could try using the arithmetic mean, and say you want to find here. I'm using the log of 2, for example, and the natural log of 2 is 0.6937 something. So you can see that just using the arithmetic mean to try to guess that magic point, you're in the ballpark. You're in the ballpark. But it turns out you can do better. You can use the geometric mean. Now it turns out this turns out to be a little bit closer.
But high.
And it's still not so great, but it's closer than the arithmetic mean. So what happens? What happens if you take the average of those? So you have one that's too high and one that's too low. What happens if you take the average of those two? And now you have 0.6829. That's much closer. So we're getting better. Now we're creating something that's starting to look like Gauss's arithmetic geometric mean algorithm. If anybody knows what the AGM is, but this is a little bit different because you see here here you say A2 equals A1 plus G1 over 2, and in Gauss, G2 would be the square root of A1 times G1. But in our algorithm, G2 would be the square root of A2 times G1. So there's a subtle difference between this and the Gauss's algorithm. And it turns out that this, you go down here and you do your arithmetic and geometric means, and the two converge to a common limit, not quadratically like Gauss does, but fast enough, and we all have techniques that I think most of us know for how to speed up the convergence. Now Ron Dorfler wrote a book called Dead Reckoning, and it's highly recommended for everybody here. It's how to get rid of the calculator entirely, mental calculation. But he has a formula for logarithms, and his formula gives a pretty darn good answer for the log of 2. And I can go farther. Now what did Ron Dorfler do? What Ron Dorfler did is he took this sequence from the Borchards algorithm and he just extrapolated it. And when he extrapolated it, the formula he got was x minus 1 times 6 divided by 1 plus 4 times the square root of x plus x. And when I saw that, the first thing that was shouted out to me is, gee, 1, 4, 1, that looks like the Simpsons rule for integrating something. What could that be integrating? So, come on, move, there. Okay, so, let me get out my, this, it turns out this is what that was the Simpson rule for the integral of. You see, because the square root is x to the 1/2, so that's the midpoint. So there's another way to get there. You can go there from high school calculus. You just take this integral, and you just transform it into this, and that works out to this, which if you divide x minus 1 by this, guess what? You get the log. So this, and it turns out this is an exponential. Now, exponential function has rapidly decreasing terms in the power series. And so it's much better behaved and a much closer fit to a polynomial than 1 over x would be. And that's one of the reasons why this works so well. And by the way, I want to thank my HP Prime for doing all the power series. It's a lot less work than doing it by hand. And I'd like to point out to everybody that's a capability that the Texas Instrument calculators, even the ones with the CAS, did not have. So once again, you apply Simpson's rule to this, and you get Ron Dorfler's formula. And if you apply Bode's rule, then you get 5 points, and you have to do 2 square roots, of course, but that's not out of sight, never underestimate the power of a square root button to propel you forward. So here's what the formulas look like. Once again, from my HP Prime. See, there's your 1, 4, 1. That's your Simpson's rule. And this is the power series of the error terms. So you see the error for Dorfler's formula based on Simpson's rule goes up as x to the 5th. But look at that denominator there. I mean, that's already a large. You're already dividing that by a large number, so that's starting to look pretty good. And then, of course, I extended that Richard's extension. Now my error term is x to the 7th, and look at the divisor for the first term. So that's really good. So looking at the first few integrals, let's say you want to take the log of e. Now remember, log of e 2.7. This is something for which the power series for log doesn't even converge. So forget about the power series. That does not converge for greater than 2. So trapezoidal is pretty terrible. The Simpson rule, we're getting in the ballpark. And once again, here's my approximation, which goes even farther. So one other comment I'd like to make: Bode's rule. What is Bode's rule? Well, it turns out it originally started life as Boole's rule, B-O-O-L, and due to a typographic fault when the Handbook of Mathematical Functions was published, the L and the O were kind of squashed together, and it looked like a D. So you see, that could have been Boole. That was originally Boole's rule. The L and the O were originally squashed together to make a D. And everybody assumed that since the Handbook of Mathematical Functions was a government publication, obviously it couldn't be wrong. It must be Bode's rule. But in fact, the guy back in the 17th century, Bode, he had this mystical rule about the spacing of the orbits of the planets and all that. Which, by a strange coincidence, did predict the orbit of the asteroid belt and I think Uranus as well. So no relation.
So it's the same rule, the same Boole as the Boolean algebra and
Yeah, Georgia, yeah, bool, it's the same bool as Boolean algebras, yeah. And, so, yeah, and also I'd like to thank Ron Dorfler for the paper that's in the proceeding. I'd like to thank Ron Dorfler for, he actually reviewed it, 2 years ago when I thought it was gonna be for the HHC 2020, which never happened. Why won't it go?
You gotta find a magic place to hit.
So what is that?
Because there is no B-O-O-L-E.
Okay, no, there it is.
Okay, yeah.
Okay, the government couldn't be wrong. So now you know how to calculate logarithms with amazing accuracy, is as long as you know how to calculate square roots. And you can respect a square root button. A 5-banger isn't, a 5-banger is way more powerful than a 4-banger. And what happened?
It works.
So what I did is basically I found a much simpler path to getting that kind of a formula, and you could probably go to a higher order Newton-Cotes integration and get even better. But anyway, that's one corner. But if you're curious about logarithms, read that paper that's in the proceedings, and that's it.
Thank you very much, Richard. You know, you have